that part of the okay. So we had talked last time about some of the broad perspective on Sheaves, some broad factoids on Sheaves. I'd introduced this nice little diagram from Tom Gebhardt's paper, together with others from Blue Light AI and elsewhere, I think, showing the an example topological space, showing data in stalks over that topological space, possible values that can be taken on by something in this location, but also showing the restriction map, showing the fact that these different areas of the topological space that are connected also have restriction maps that are connected here, and those areas provide some constraints on the set of values that can coexist in these different areas. Okay. We had also talked last time about the sheaf of continuous functions, and I'd like to revisit that today. But we had started down the path of discussing last time properties of pre-sheaves and properties of sheaves, and I really wanted to clarify some points from that. So I think I'll come back to the examples. But I do want to situate us again squarely in this issue of the spaces in which we're working, the specific categories involved, and the specific morphisms within those categories. In fact, the types of morphisms. So you recall that a pre-sheaf from a category that represents a set of opens. This is a priori category or post-set category. This is a category where objects are sets and morphisms are what? Do you remember in this category of opens? Inclusions. Inclusions. So it looks something like this, where this set is included in this other set. Remember that? This set is included in this other set. That's the category we're dealing with here. This category set is a category with sets as objects in what as morphisms? In set, what are the morphisms? Functions. That's right. Okay, so if we have a pre-sheaf from this topology related priori that describes the topology and the relationships between open sets and the topology, like that regions, there are regions U1 and U2, and they're inside U, and there's a region U1 intersect U2 that are inside of both. If we imagine a pre-sheaf from that into set, it assigns to each object in this category. What's an object in this category? It's a set. In fact, it's an open set of the topology, and it maps it into some set, right? In the category set. And we call that the local section over U, over open set U. But if there's a morphism in this category, remember, what are morphisms in that category? They are inclusions, right? If we have a morphism here, it's an inclusion. That's why it's shown as a monomorphism. It's like this is a subset of this. If we're dealing with these, if these are indeed sets, this is a subset of that, right? That gives a restriction map from U to V. Why is it contravariant? Why is it? Sorry? Yeah, this is the pre-sheaf categories op. So So this is inside U, and we get a restriction map in the opposite direction, right? It's contravariant because this goes from V to U. This goes from F of U to F of V. Okay. That comes from this being a pre-sheaf. Are we comfortable with that? Right? It assigns an object of this to a set. It assigns a morphism of this to a morphism between sets in set, which is a function, but in the opposite way, in the reverse way, right? I think you'll further agree that if we have two morphisms in a row, and really by all accounts, I should take this so I don't have to keep on dizzyingly going back and forth. I should take this and I should put it in the next slide. If we have two morphisms in a row, if we have something like V1 is inside V1 and union V2, so open set V1 is inside open set V1 and V2, and open set V1 and union V2. And if open set V1 union V2 is inside U, right? You remember the idea of a functor? Any functor, but certainly a pre-sheaf, honors composition, right? It honors composition. So if we can either compose here and get a map from V1 to U, and then map over and get a restriction map from what to what. If we compose in this category, so we get a morphism from V1 to U. Basically, V1 is a subset of U. We map that over and we get a restriction map from what to what? F of U. F of U to F of V1, because it's contravariant. By contrast, we could alternatively, and any functor, this is true, right? We could map this morphism over, get a restriction map from V1 union V2 down to, so F of V1 union V2 down to F of V1. And we can map this one over and get a restriction map down from U to F of U to F of V1 union V2. And then we could compose in that category and get one from F of U to F of V1. Mm-hmm. Now, I noted that for a given object, particularly in sort of subobjects, we called F of U, like F of V1, to be a local section over that. F of the entire space, X, if we had some entire space X, and these are the open sets of it, F of X is called the set of global sections, a set of consistent pictures of the behavior going on across the space. We comfortable with that? Okay. Now, I'm going to come back to this, but I want to, having rehearsed that with you, I want to talk some about what's going on categorically here. Okay. So specifically, we're going to be dealing with two different categories. And I really should have a diagram of the whole darn thing. Oh no. Okay. That's where I want to go. I will show yes, it's this one. It's what I'm looking for. So this is our category with the pre-order on open sets. We comfortable with that? This one here? These are inclusions, right, of sets. We were just talking about it. We good with that? And this is the result of mapping functor, we're going to call it S here, this pre-sheaf functor, over to set. This is the category set, and so here objects are sets. Here they were sets. Here they're sets. They're sets of local sections on this open. So this is an open set. It's mapped over to the local sections on that open set. But the morphisms here again are what? Inclusions. Morphisms here are functions, so particularly restriction maps. Okay. So here they are functions. And I want to talk this through a little bit further because there's a chance that this will induce an aha moment, either when the first time you listen to it or if you listen to it later. So these are inclusions, right? Okay. So I want you to reflect on some facts. First of all, do you remember the notion of a limit? Do you remember that? We talked about it with products, but particularly with pullbacks. See, the idea here is that we have some diagram and we map it to some category where each of these objects from the shape category, the index category, gets mapped into a particular object, which these morphisms get mapped into. And then we are seeking an object, a single object, which may not itself be in this diagram, maybe outside, that has a morphism down to each and one of these objects, such that it makes all of this commute, all of these triangles commute. Everything in this cone has to commute. And you could think of it, you could be excused for thinking about it as a situation where we are trying to find, like maybe these are different numbers in a set, in which case they wouldn't, maybe one number is less than another, et cetera. And this is going to be like the minimum of those numbers, for example. If this were a set of an infinite number of reals, the minimum might actually not be, the lower bound might not be in that set. The lower bound, the infimum, might not be in that set, right? It might be just below it. So maybe we have a series of numbers that are like 0.1, 0.01, 0.001, 0.0001, et cetera. And this is like 0. It's the sort of the lower limit. So I'm trying to draw an analogy here between a limit in that we might have been talking about in topology section versus here. Alternatively, this could be a limit of another sort. It could be, for example, a limit associated with a pullback, right? Well, I'll be.
Do you have any questions?
Yeah, I dressed up as a nerdy professor. Yeah. So anyway, this if these were if this diagram here were of a shape, okay, I don't have actually a nice picture of it, but if we had a shape associated with an object and morphisms into it from two directions, this would be called the pullback, right? This is the pullback. So this idea of limit may be familiar with you. And do you remember the idea with the pullback was that the pullback of two sets over another set gave us a set itself that was a subset of the powers of the Cartesian product. I don't know if you remember that, but it would be like all compatible pairs of A and B, like all pairs of shirts and pants that match, right? Okay. Okay. So I'd like to talk about this. If we have a diagram in our pre-order category for our topology, right? We have something like this, right? And we have open sets U1, U2, U3, etc. And we have U, such that these all cover U, collectively cover U, such that U is the co-limit of the diagram. In other words, these all come together. Do you remember the idea of a co-limit? What did that involve? What was an example of the co-limit? Push out is a good example. What is a co-limit in this category where you have set and you have inclusions? Union. So if U is like the union of U1 and U2 and U3, right? It includes U1, it includes U2, but things that are in common are merged or identified, right? That's what union does, right? It doesn't add a thing twice. Disjoint union would add, if there was a thing in U1 and it was another, and it was also in U2, would say, this is U1's version, this is U2's. But a union is a co-limit. That's like these things combine. Do you get that? So this is a co-limit here, okay? U is the co-limit of this diagram. It's the union of all these things. And remember, these are inclusions. And this is a pre-order category. Or you can say a post-set category. All paths here all paths from A to B are equivalent. So if we have a path from U1 union U through U3 and up to U, that just says U1 intersect U3 is a subset of U, right? And it's the same information, it's the same as going up U1 union or intersect U3 through U1, and then that U1 to U, that also says U1 intersection U3 is a subset of U, right? So all these paths commute. Do you agree with that? I mean, it's a pre-order category. It's a thin category. That's true for any thin category. All these paths commute. Do you agree with that? Okay.
Does the diagram have limits?
This diagram here has, this particular diagram has, I think this is going to be the limit, but I don't want to, I think this will be the limit of it here. This will be a co-limit, but we don't have to worry about the limits fundamentally. Where we have to worry about limits is in a moment, but it's not in this category. So we're going to be passing it through a pre-sheaf, but more than that, we're going to be passing it through a limit preserving functor. Okay. A limit preserving. Now, this is limit preserving from this category up into set. It's going to preserve limits in this category up to sets. What are limits in this category up? They are what in the category itself? What's a limit in O of X up? It's still U, yeah, because it's up. So a limit in O of X up is a co-limit in U of X. So U is a limit in U of X up, okay? Okay. So we're going to concern ourselves now with not just pre-sheaf functors, not just generic functors of this sort, but limit preserving functors. Okay. Okay. Now, so if this is limit preserving from U of X op, O of X op, this U is going to be mapped into a limit over here. So what this is saying is f of U is the limit of this diagram. And if you understand that, you're going to get the essence of Sheaves. So I want you to unpack this. The fact that this is limit preserving and the fact that this is a colimit, therefore in O of X op, it's a limit, means that it gets mapped to something that's a limit here. What does it mean for it to be a limit here? We just talked through what is a limit. What does a limit mean? This is the apex up here. That's what f of U is. What does it mean that this is a limit? It means that all these paths beneath it commute, which is exactly what's implied here, because these things, all these paths commute, right? And that any functor has to honor composition, and so all of these must commute here. But the fact that this is a limit of this diagram basically means that, yeah, that all of these maps underneath here, all of the maps here in the cone commute. Now, this is of great significance that all of these commute. That gives the essence of the sheaf property here. Now, I'm going to take this one step further to align it with this idea of an equalizer. Okay. So the fact that this is a limit actually gives you the information you need about the sheaf property here, because it means, for example, going f of U to f of U1 to f of U1 intersect U2 is equal to f of U to U2, and then over to f of U1 union U2. It's saying these paths have to commute. The fact that this is a limit of this diagram implies these paths have to commute, which means this restriction map has to map down from here, has to equal that one map down from here for these intersecting regions. Now, I'd like to unpack this a little bit more in a way that's really important for a further definition of a sheaf. So one definition of a sheaf, I'll note, that you'll find is that it's the limit, involves the limit of a diagram like this. That's the essence of it. It involves the limit of a diagram here. It actually talks about it being isomorphic to it, but fundamentally it's the limit of a diagram.
Read this book as well.
Did you?
Yeah, because I want to know.
This is Justin Curry's.
Yes.
Thesis.
I want to know like sheaf, sheaf, co-sheaf, pre-sheaf, co-pre-sheaf, and the relationship among them.
Yes.
So I read that instruction part.
Yeah. Okay.
2 days or 1 day to read everything.
You are an extremely fast reader if you read that in like a day or a couple of days. That's super impressive.
No, the first couple chapters.
I see. Yeah.
It's a thesis, right?
Yeah, it's a thesis. It's a dissertation, and it tries to systematically lay out the ideas.
Yes.
Yeah. Okay. So the fact that this is a limit tells us about this key sheaf condition, because it means that we have to have this restriction down, like from this to this to this, to equal this restriction down to this. And what this is saying is that what's shown here over U2 and what's shown over U1 are not independent. They're not solitudes. What's assumed here and here have to be consistent in the sense that if you go down here from f of U2 from this data and you restrict down to this intersection, it must be the same as what if you assume this and restrict down to here. Just like in a pullback. So let's see if I have that up here, my pullback slides. But in a pullback, doesn't look like it, but I'll call up my pullback slides. But in a pullback, you also have this matching restriction, right? With pullbacks, you recall that you don't just have all pairs of AB, you have all pairs of AB that have to be consistent with what they presume about their value of C. They have to match up in how they map to C. This is a limit of this diagram. This is our diagram. We have a limit of it such that all these components commute. And that's what our pullback is. Here it makes this commute. So we could think of it like this. The V is kind of above this, and it makes these commute. Makes if I go to B and then to C the same as if I go to A and then to C, and same as if I go to V directly to C. That's what a pullback is. And what I'm telling you is that a sheaf is that in this situation here, right? It has the flavor of a pullback because if I go here and then there, it has to be the same as going here and then there, right? Right? That's it gives a little bit of a flavor of a sheaf. I mean, both are limits. That's what distinguishes them. And what this is saying is that a sheaf is not only any old value here. It's a value here that makes all of these paths commute. They all have to be consistent when we restrict them to smaller areas. What's assumed for the global section has to agree with what it implies for all these different subsections through different paths of it. All these things have to agree with this. Are we comfortable with that? Just like with a pullback, all, the shirts and pants all have to be the same color. Okay. Now, I'd like to take this one step further for another high-level definition. I think we will all agree that if in this category we have something like this, U1 going to U, so something like this, for example, right? If you have UI, some UI, say U2, going up to U, if we map it over with any pre-sheaf, we get a restriction map, right? And I'm going to label that row for restriction. It really helps if you learn to realize, at some point you realize in category theory, a lot of things are labeled based on their first letter, like you'll have R for, this implies R, it's a R thing, it's a restriction. And similarly, you'll use lambda for L things, like a left thing versus right thing. Okay, so this is our restriction from f of u to f of ui. Are we good with that? Okay. And if we have a bunch of these things, each of them would have a restriction, right? Like if we pass this through any pre-sheaf, from opens up, we get this, right? You get a bunch of those things. Now, this might start to remind you, what does this start to look like if it's got all these maps down, what else has lots of maps down to its different pieces, to the different things that make it up? What type of categorical construction has lots of maps down? It's one of the first universal constructions you saw. Sorry? Well, it's a type of limit. What is it? Product, right? Product is these kind of maps down. You remember that? And so, do you remember the universal property of a product? Universal property of a product said that, hey, if you have any other object, say f of u, that has these maps down to this, then the product, then that object will have a unique morphism to the product of these things, such that this is unique. Do you remember? And such that the map from f of u to u1 is the same as e and then pi of u1. Do you remember that with the universal property of a product? We had this property that any other object that has these maps down could be expressed in terms of this product through your unique morphism. That was part of the rules for a product. I'm not sure if, well, yeah, I mean, remember, this was the universal rule for a product right here. I will show it. Remember this? This is the universal rule for a product, universal property. If you have any other object that is maps down to here, A and B, the product is the one that factorizes all of them. It's the most essential. It's the most minimal. It's the best of those, the most essential, quintessential one that is maps A and B. Any other can be expressed in terms of the product, where this morphism and then this one is the same as this morphism and then that one is the same as that. Do you remember that? So I'm saying, if you have f of u like this, we can express it in terms of a product. Now, this may seem abstract nonsense, but it's not. Look, what is this morphism? What does this morphism do? Okay, so this is the product of all these things. Okay, fine. And you project down from there. What is this morphism going to map to? Well, what is it going to map to? The product is going to have something for f of u1 in it. It's going to have, this should say f of ui, the product of f of ui. Okay, that's my bad. Let me see if I have that still around. Yeah, this should be, sorry, folks. This should be f of ui there. Okay. That's what it.
What weapon are you using to create
Quiver. Quiver.app.
I tried to use Google slides, but to create somewhere.
Yeah, look at this. It can produce it as TICZ.
Okay.
This is for LaTeX, yeah. So it can produce it. It could also produce a URL, so you can go back to it and save it. But yeah, it's a really nice little editor for these sort of diagrams. Okay, well, let me get rid of that. Hey, come on. Okay. There we go. So we have something like that. So what I'm saying is that any diagram like this to the left can be re-expressed like this. What would this E be here? What would it map for the first element f of u ui? What is, so E itself is going to be a product of maps. What's the first element of the product map that maps f of u to f of u1? What is it going to be? Well, it's just going to be row u1, u1. What is it going to be mapped down to for the second thing here? So what I'm telling you is that E itself is a product of row U1, row U2, row U3, row your boat gently down the stream. No, it's like row U U n minus one. Right? So here, that's what E is. E is just the product of each of these things. And then we project down to each of these. Are we comfortable with that? That anything like this, I mean, it's by the universal property of the product, this must have a unique morphism, but the unique morphism is just the product of these. Are we okay with this? Okay, now, if we're okay with it, we need more conditions. Is this enough to express what f of u is? That it's just this? No, we need the commuting conditions, right? Well, to get the commuting conditions, to restrict, what we assume about each of these, what we assume about this, in other words, we use this construct called an equalizer, okay? And the idea here is that, and I tried to express it for sort of two components, but I think I'll cut to the chase. What we have is this. What we have is, so this is what we just expressed. We have this big factorized by product. This is what we had down at the bottom of that last diagram. We had these things down at the bottom, right? Each of these, like f of u1, f of u2, f of u3. That's exactly what this is here. So this is okay, we can factorize it by this. What is this map here? Well, it's a restriction map. Where does it come from? What allows us to be sure that we have this map? Well, over in this category to the left, this category here, we have an inclusion from like U1, U2 into U1 and an inclusion into U2. That means that when we map them with this functor, we get a restriction map down. Are we comfortable with that? Okay, watch that. That's exactly what this is here. That's the restriction map down. We had it in our category, our O of X category, our category, pre-order. We had an inclusion map that said U1 intersect U2 is a subset of U1. And now we map it over with our functor. And we get a restriction map down to it. We good with that? So this map is just from that. This map is similarly for J. But more generally, I mean, you could express this more generally as, look, this is an equalizer. We want this. This is a key idea. We want this to be able to, for any intersection UI and UJ, we want the map down to it that occurs as a result from going through, so from this product, going from UI to the intersection of UI, UJ, to be the same as, so that's P, to give the same result as Q, the map from going from F of this product down to this in restricting here. We want those to be the same. That's what do you remember what an equalizer does? It basically, remember we saw equalizers before? I should really have called my equalizer slides up, but I ran out of time. Equalizer, right? Here, and I guess they would be in this category here, or this set of slides here. Let's go look for equalizer. Come on, here we go. Do you remember this characteristics of an equalizer? This is our equalizer. And we went through it on the board. Here we go. Let's go remember our equalizer. Okay, come on. Okay, here's the equalizer shape, right? Do you remember the product of the basic property of an equalizer, the characteristic? What did it involve? Well, E is a subset of X such that what is equal to what? Yeah. So E is a subset of X. So it's a subset of the elements of X such that let's call a subset of X be little x. E includes all the little x's such that f of x is equal to g of x. Do you remember that? Do you remember that? It's the subset of them for which this equals that. Do you remember that idea? We actually did it up on the board at that time. I don't know if you remember, but we did a little exercise like this where we said, okay, here's our x, here's our e, and we have here so E is a subset of X such that the two morphisms match up. So I think this was showing one morphism. This was showing another morphism. Actually, sorry, we were showing morphisms in different colors. One, like this was one morphism F was in red, right? And one morphism was in black. That was back when the black was still around. When the black was still alive and kicking. And we said, what's the equalizer? What's the subset of these for which these two functions map them to the same elements? And we said, does it include A? No, because A is mapped by red to 0 and it's mapped by black to 1. So it does not include A. Does it include B? Well, B is mapped by red to 1 and by black to 1. Yes, so then our equalizer includes B. It's a subset of X, the elements X, that are mapped the same. Does it include C? Yes, both map to 0, so it includes C. Does that make sense? So what we're saying here is that for our, maybe I should, for future reference, copy that slide also over here so I can remind us. Okay. So what I'm saying is the equalizer here is saying, hey, f of u, think of it this way. Imagine that this is all products of pants and shirts in your home. This is just those pants and shirts that are the same color. P maps a pant to its color. Q maps a shirt to its color. And these two have to be equal. And this will, if those are what P and Q are, this will be the set of all pants and shirts of the same color. Right? Kind of pullbacky thing. And it's similar here. It's like P, though, here describes the map down to U1, F of U1 union U2 through F of UI. Q describes it through F of UJ. And those need to agree. In other words, whatever we assume about f of ui has to be consistent in terms of what it shows for the intersection with uj as what we assume for uj. Those two must agree, is what this is saying. So if we go back to this, the equalizer there is just making sure for any pair of things here, any of these, that if you consider them pairwise, their mappings down to this next level down agree that they are all aligned, that they're all coherent, that they're all consistent. And that's what this being a limit does. Remember, the idea of a limit was all of these things commute. All of these paths commute. That's another way to see it. You can see it as a equalizer factorized by the product in this sort of way. Or you could see it as just a limit of this diagram where all these paths have to be consistent in what they posit for down here. So if you take a given point in U and you consider restricting it to, you consider the behavior over that point in f of u, that has to be the same as restricting the behavior for all of u down to u2, and then restricting that down to f of u2 intersect u3. That has to give the same result as if you take this all of u restricted down to u3 and restricted down here. They all have to agree with what's going on down here. They all have to agree with all the points. They all have to be consistent. And that has to do with these two sort of views of this as limits or as equalizers. Sheaves are equalizers of a sort. They are kind of like this, having this product, but the product, this is kind of producty, right? But the product is such that everything has to agree in terms of all of its restrictions. That's one way. Or alternatively, if you're comfortable with the idea of a limit, you're comfortable with an idea that makes everything commute here. That's what a limit is. Then you can deal with it. You could just think of this as the limit of this diagram, and that's also comfortable. And the key thing that enables that, it says limit preserving functor. It maps this colimit in O of x, this pre-sheaf category. This is the colimit. It's a union of all these things. It maps that. It takes its op, that's a limit, and it preserves that, and it maps it over to a limit here. And the fact is, a limit here makes this all work. It makes this all commute. So maybe limits are nothing too bizarre. I mean, we've seen them quite a few times. Do you remember if we had a category where objects are numbers and morphisms express, morphism A to B expresses that A is less than or equal to B. And we have a set of these objects, A, B, C, D. What's the limit of that? Well, it's the lower bound. It's a single thing that is morphisms to all of them, such that they all commute. Well, they're all going to commute because there's only one one way from going from any A to any Z. One just says A is less than or equal to Z. So they all commute. So it's the minimum. If we have a category where the objects are sets, and we have the morphisms from A to B mean A is a subset of B. In other words, A is included in B. What's the limit there? Well, it's the thing that has sort of morphisms to all those things such that they all commute. It's pre-order because A is a subset of Z. Is regardless of the way you go to it, it's the same. So it's the intersection. If we have a diagram where objects are numbers and a morphism from A to B means A evenly divides B. A goes 5 goes into 30 an even number of times. So there's an arrow from 5 to 30. What's the limit if I give you a set of numbers there? 5, 10, 15. What's their limit? Yeah, it's common divisor 5. Because it's the thing that has morphisms to all of them. Right? The closest thing kind of upstream of them. There may be other, like one has arrows to all of them, but this is the closest one, right? Yeah, so here, this is our limit. It's the limit of this diagram, and it has kind of a pullbacky feel. It's not just the product of these, it's the product of these such that all these paths commute. And that is exactly what is being said in this diagram. It's the subset of the product, just like pullback was a subset of a product. The pullback of your pants and shirts that are the same color is a subset of all pairs of shirts and pants that you have. And it's the specific subset such that the color of the pants maps the color of the shirt. Here, this is the specific subset of f of ui of what you assume is going on in the ui, all the ui, such that if you restrict it to the intersection of ui and uj, it's the same as through ui, it's the same as going through uj and restricting it to that. Does that make sense? Okay, now, so a sheaf, we could go through slide after slide after slide, but the point is that the sheaf has a sensible feel to it as a limit. It's a limit that makes everything agree on all of its subsections. And if you can keep that in mind, you should be able to understand this. This is the data associated with each of these spaces in the topology. Right? And this needs to all commute. If I go and I ask, I follow a point here, and I follow it down here, and I follow it down to something that's in this, it needs to be the same as if I go here and follow it down here. It all has to line up. Going down this way and this way, restricting has to give, for the overlap, has to give what I get here in restricting here. And the same thing for this, and the same thing for this, and the same thing all the way down. And if we have that, we have the subset of all behaviors over U that all are consistent in their picture of what's going on. across the space. Or alternatively, if we want to think of it, let's think of it for, I was creating this. Okay, let's think about this for some exercises. I'm gonna stop this.